Good morning, you 11s. Good to see you guys. Right, guys, I love the fact that, oh, Ruby's in. Oh, Ruby, I'll amend the register later. I love that Ben's like, I'm first. And he wasn't. That was amazing. I love the fact that, oh, Ruby's let's in. Turn off that. Ruby, I'll amend the register later. There we go. Get rid of that. At least I know it's all running. Right, share screen. Let's crack on. Today is Equilibrium Lesson 2. Let's get rid of my face. Don't have my face. Hide. Share screen is on. Right, then I'm going to then stop my camera. Oh no. Oh no. Are you ready for it to crash? Oh, it's made it. I have to say, it genuinely makes a difference though. So, okay, guys, today's lesson is Equilibrium Lesson 2. Yield a position and understand position. Position and yield. Okay. Boom. I like it. Zoom, zoom. Okay, so today's title, guys. I didn't give you any homework from last lesson, I believe. Yeah, we just talked last lesson. We were talking about reversible reactions. We mentioned the term closed system. Yeah, and we were just kind of defining what these were and when they happen, and this idea that some reactions can go backwards and forward under the same conditions. And today we now look at those reactions in a bit more detail, and we now need to go from this. Is it okay if I leave the meet? My laptop is passing away slowly. Your laptop is passing away? Oh, your laptop's dying? Sure. Do whatever you like, Rubes. Okay, so 2 learning objectives today, and that's all I need to do. So I'm hoping a great lesson. I highly doubt it, but still. So, okay. So GCSE Equilibrium Lesson 2, Dynamic Equilibria. So, by the way, I'm actually going to change the letters. Oh, maybe not. No, it's all right. It doesn't really matter. Okay. Equilibria and equilibrium, kind of the same thing. They don't really make the distinction at Edexcel, at GCSE especially, RIP laptop. Okay, so now that we realize that some reactions are reversible, we now need to look at this in a much more detailed scenario in understanding what's actually going on. So the first thing I'd like to do is I'd like you guys to, we just need to go, okay, so the definition of a dynamic equilibrium. So as of last lesson, we need to realize that we need a closed system. Yeah, so I need to create a box. And in that box, what I'm now going to do is I'm now going to put in some reactants. Let's say I'm going to put in particles A, and I'm going to put in particles B. Let's put in 3 A's and 3 B's. Right. Now, so my equation now becomes A plus B goes to, it's a reversible reaction going to AB. Yeah, so it's nice just to kind of try and understand this a little. So on this side, we've got 2 particles going in. We can actually look at that in terms of moles. We've got 2 moles going in. And then when they combine together, they actually form only 1 mole of a solid. Yeah, so we've got a decrease in moles because the particles are joining together. So what we realize is this arrow here means reversible. Common mistake is for students to call it equilibrium, and it's not. It means reversible. Now, at the beginning of this reaction, I put in 3 A's and 3 B's, and it's nice just to say that this is where all chemistry starts. Yeah? It starts where I've added in 3 A's, I've added that to 3 B's, and at the minute, yeah, I have 0 ABs. Yeah, so I've added reactants. It's nice just reminders of these words. We've added in our reactants, and we've got at the start of any reaction, we've got 0 products. Okay, so now what I'm going to do is I'm going to press the big go button. Yeah, I'm going to press start on my reaction. Now, as time progresses, what happens is every now and again, an A and a B will collide hard enough with the sufficient energy, with the activation energy, yeah? And it's going to form, so these guys are going to vanish, and they're going to form AB. There we go. So what we could say is this happened after 5 minutes. So after 5 minutes, my A and B has dropped down to 2. And my product has now gone up to 1. Now, what that now means is, now if you'll notice, I'm doing something clever in my diagram. Because at the beginning, I only showed the forward reaction. Only forward arrow. Now, you'll never have to do this in there. This is only for understanding purposes. Only forward reaction can happen. And that, the reason being, is there's no product to turn back into the reactants. Now, what's happened is, now in order to try and keep this to scale, the top reaction is going to slow down. So if we make this one here nice and large, yeah, this one is now smaller. So the top reaction, if I should color code this, the forward reaction was blue. So the forward reaction has slowed down. Yeah, forward reaction slows down. Now this is, of course, not to equilibrium, but down to kinetics. It slows down. The concentration of reactants of A and B decreases. A plus B drops. I'll put drops. Concentration decreases. Therefore, fewer collisions. Frequency of collisions decreases. Freak of collision decreases. Yeah. Therefore, fewer successful collisions. Yeah. Successful cols. Yeah. So the top reaction slows down, but now the backward reaction has now appeared. The backward reaction starts happening. Now, it's not happening quite as fast as the forward reaction because I've tried to make them different sizes, but the backward reactions can now start happening. Now, what this means is that, once again, the A and the B can collide to form another AB. But at that point, the AB could split apart to turn back into A and B again. So what we realize is we've got the reaction is happening in both directions all the time. And I'm going to show you an animation of this. Just to show you an animation. Documents. This is going to take a while. Sorry. Back up. Pen drive. Back up. Teaching file. GCSE. Probably year 11, unit 2. Nope. Equilibrium. Where is it? I can't see equilibrium, which is very irritating. Equilibrium, reversible reactions. There we are. Allow. Oh. Don't want that. Allow. Right. Okay, guys. So, as you can clearly see, in this particular reaction, my reactant is white. And at the minute, I have got one. This is where I should screenshot this, full screen snip. I have got at the beginning 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've started off with whites and I have 10 of them. Now it's going to split. Yeah. W is going to decompose. And it's going to decompose into, I think, red and blue. So at the beginning, I have 0 red and blue. This is the start. Yeah. So at the beginning, the forward reaction is the only one that can happen. So let's now look at what happens when I press start on my big start button. So a white has decomposed into red and the blue. Right. So the two reactions are happening under the same conditions simultaneously. Now, what this now means is equilibriums are kind of special because in reality, the reactions never stop. The reactions are permanently happening because they're going forward and backwards at the same time. Now, this begins the process of building my definition today. So I'm going to pause that. I'll reset it just for fun. And then go back to here. Right. First learning objective, definition of dynamic equilibrium. Okay, so let's put a definition in. Oh, way too big. Okay, definition. Change my color. Dynamic equilibrium. Okay, now this has major points in it. Sometimes, by the way, this question gets called the features of a DE, dynamic equilibrium. Yeah, features of. And feature number one, the forward and backward reactions. I don't like that it's slanted. It's making my eyes go funny. Sorry. Features number one, forward and backward reactions are always occurring. They never stop. They are always occurring. Okay. Now, the next thing is, the next bit, which is a bit more tricky, because this is where my diagram came in handy, and I'm gonna make this into a bigger diagram. Let's start off with, let's do this similar process and go. So we started off with whites, and it's going to break apart, and it's going to form reds. It's going to form reds, and it's going to form blues. Now, at the beginning, we had 10 whites and 0 reds and 0 blues. This was the start. Now, what we realize is the forward reaction is the only one that can happen, and the forward reaction is going to happen fast. 10 Ws, that's high concentration. Yeah, now what's going to happen is, at minute 1, I'm going to press go. Minute 1, that drops to 9. The top reaction slows down, and the bottom reaction starts. I now end up with these guys. Okay, next, minute 2. Another one decomposes. That one starts to slow down. That one's speeding up. 2 and 2. Next, and by the way, I know that the numbers don't add up. I know people really struggle with that. They don't like that concept. But I'm making, remember that every 1 W makes 1 red and 1 blue. So just bear that in mind. At minute 3, look what now happens. Minute 3, the equations, the reactions are now in a very special point. We have now reached an equilibrium. Now, the point I'm trying to make with that split of that name and the misspelling deliberately is because the word equal is telling us something. It's telling us the second feature of a dynamic equilibrium. The first feature is that the forward and back reactions are always occurring. They never stop. Feature number 2, at equilibrium, at equilibrium, the rate of the forward and backward reactions rate of the forward and backward reactions are the same. The rate is the same. What that means is that what's going to happen, I'm just going to put this on the chat. Guys, so this has reached an equilibrium. So what are my numbers going to be at minute 4? What are my numbers going to be now, guys? I wonder who's going to get that on the chat. So really, this is going to, if you understand what I have said, you will be able to tell me what these 2 numbers are. Or these 3 numbers are. What are these 3 numbers going to be now that we have reached equilibrium? I seem to have, Love a drink, that'd be great. But tea would be lovely. Or no, yeah, tea would be good. So, con, 2 and 2, con, for a start, there's 3 numbers. Yeah, that number, then an arrow. Well, by the way, Rue's given me the right answer, just so you know. Con says 8, 2 and 2. Ruby says 8. Nope, that's not correct. By the way, it's not your fault. It was, I think the animation might have let you down. Rue's got the right answer. Ashley's done the same thing as well. That's not correct. Once the reactions become equal. Wait, confuse. You're going to kick yourselves. Rue, well done. It's exactly the same as it was at minute 3. Shanley, well done. Tong, well done. Great job. Oh, wait, keyboard slam. Love it. Ben, oh, Ruby, the same? Tong, hold up. Oops, I get it now. Cool. The reason being is, once they are going at the same rate, I'm going to have these turn into this, but this turn into this at exactly the same pace, which means the numbers don't change. I can leave this running now for half an hour and the numbers become static, and this gives me my third feature. Once this happens, notice my changing colors. This has been awesome. I love this. Yeah. At equilibrium, the concentrations, I'm going to capitalize it, the concentration of reactants, damn it, reactants and products remains constant. Concentration remains constant. They will no longer change. Yeah. Now, chemistry is cool. Oh, Ben, that's nice. That's really cute. So, guys, here are the 3 features of a dynamic equilibrium. I always like to mention, by the way, that it has to be in a closed system. It's always a really nice one to mention that, but it's not actually a feature. Yeah, the features are the forward and backwards reactions are always occurring. At equilibrium, the rate of the forward reaction is the same as the rate of the backward reaction. And at equilibrium, the concentrations of reactants and products remain constant. Yeah. Now, can I just point out, those people in the room who are going, hang on a minute, Mr. Duncan, I found your animation confused me. Yeah, because when you look at this, what you realize is the numbers are actually fluctuating all the time. But this is because we've only got 10 particles of white. If you put in 1,000,000 particles, in fact, you put in Avogadro's constant, 6.022 times 10 to the 23 particles, the number of fluctuations is so small, you can't see it. Yeah, it just becomes constant. It becomes effectively constant. You can't see those tiny changes because the rate of the forward is the same as the rate of the backward. I understand. In reality, there's going to be an average. Yeah. I want to show you this from a graph perspective, which is really cool. So what's going to happen here? Okay. Oh, before I do the graph bit. Oh no, I can do the graph bit. Right. So I don't want to do the graph bit yet because it's gonna look confusing for you guys, and I don't want to do that. So okay. So now the question next is Okay, I want to do the graph. Graph. Okay, so what I'm going to do is I'm just going to simplify the graph a little bit. So we know that the reactants will always start at the top because we always start off with 100. This is the reactants at 10. And at the beginning, of course, we have no products. Yeah, no products. And the products are at 0. Now, what happens is when the reaction starts, the reactants drop. Yeah, and you can get to see a really lovely rates of reaction graph. It decreased the fastest at the beginning because it was steepest. Then it starts to slow down, and then it stops. Yeah, but the thing is, we now know in equilibrium, the reaction never actually stops. There we go. So this is our equilibrium. What's happened is the reactants have decreased. Reactants dropped. Reactants decreased. And the product increased. Product increased. But then it stops. And what you realize is the equilibrium was established at that time. If this is time on this axis, let's say minutes. Yeah, the equilibrium was established at minute 6. And this is because the graphs have leveled off. They're no longer changing. They're horizontal. I'm sorry that it's not a perfect line. There we go. Yeah, it should actually match. There we go. That's better. So there we go. So they've stopped changing. At this point here, this time here, was where the equilibrium was established. Because you can clearly see that the products are increasing, the reactants are decreasing, then all of a sudden they stop. So this here shows us, this level bit here, shows that the concentration, not doing very well on my writing today, the concentration is now remaining constant. Concentration is now constant. So equilibrium has now been established. Okay, so the next question that I need to answer. So now that we've got, by the way, I need you to learn these, guys. Learn these. The features of a dynamic equilibrium, or just the definition. Learn. Love it. So, okay, now that we've picked up that, I can go to my learning objectives and go tick. There we go. Next, position and yield. Okay, so at this point, I'm going to go back to my, there we go. Okay, so equilibrium was established. In this particular case, it was established at minute 3. Now, we need to talk about this idea of position. And you know what? Let's do some new notes. Let's go. Equilibrium position. Okay, so what we're now going to do is we're going to look at a series of different equilibriums. So let's go for equilibrium number 1. We're going to go A plus B goes to C. And I'm going to tell you at equilibrium, I've got 3 of those, and 7 C's. I like it. Okay, equilibrium number 2. I'm going to take D, and I'm going to take D, and I'm going to break it down to make E and F. And I'm going to tell you at equilibrium. See what I've done there? At equilibrium. I know it's actually, I've put at reversible, but you get the point. So at equilibrium, I'm going to have 8 of these, 2 of these, and 2 of these. Yeah, I like it. Don't actually need the plus, by the way. There we go. And then equilibrium number 3. I'm going to go for G. G plus H goes in a reversible reaction to make I. And I'm going to tell you that I'm going to make 4, 4, and 6. Okay. So now the first thing, this is at equilibrium. I like it. So the first nota bene, we're going to put down nota bene. Equilibriums never, notice, never, ever lie exactly in the middle. So students often think, and I totally understand why, I get it, because students kind of imagine, you know, this idea of a seesaw, and, you know, you put one person on one side, you know, and when it's balanced, the balance would be 50-50. That's what they imagine this is always going to be. Wait, Mr. Duncan, I'm like 4 minutes behind on the vid, but what's the difference between dynamic equilibrium and an equilibrium? The answer is they're exactly the same, Isabel. They're actually the same, but the word dynamic is just one that they tend to include. In fact, they should always include it, but sometimes they just don't bother. But they actually mean exactly the same thing. An equilibrium is a dynamic equilibrium. It's just sometimes they don't use it and sometimes they do, but they're the same thing. Isabel, I'm so glad you asked. Thank you. Yeah. So students think that equilibriums are like 50-50. Yeah. Oh, well, when you get to the middle of the reaction, it's going to be like this. That is never true. The chances of getting an equilibrium to be exactly 50-50 are 0. It just will never happen. It's just ridiculous. You could try and push it to the middle, but you wouldn't want to. And we're going to cover pushing it later. So number one is they're never in the middle. What that means is we can talk about where their position lies. So if we look at reaction number one, so in this case, what we're going to say is this equilibrium lies to the left. It lies to the left. Sorry, it doesn't. No, it doesn't. I'm an idiot. Ugh, left. Right? Always check your left and right, guys. I drive, and it's a nightmare, honestly. I take left when I should take it right all the time. So it lies to the right. So this is this idea of position. So its position, I'm going to write over here, position. The position is that it lies to the right. Now I'm going to ask on the chat, Ashley, do you think that's a good thing or a bad thing? Is this a thumbs up or a thumbs down? Is this good or bad? Let's look at the next one. So this equilibrium, I'm going to ask to Kieran. Kieran, which is equilibrium number 2? Where does it lie? What's its position? Just having a sip of my tea. Oh, it's roasting hot. It's actually quite nice. Well done, Kieran. Lies to the left. Perfect. This one lies to the left. The position of this guy lies to left. Now, I'm still waiting on Ashley's response. It's good. Thank you, Ashley. Lying to the right is a good thing. So I'm going to put good. So, Ashley, can you tell me why you think it's good? The answer is correct. It's a good thing. And then I'm going to ask Kieran. Kieran, do you think lying to the right is a good thing? Lying to the left is bad. This is a bad thing. The question is, why? Why is it better to lie to the right than it is to lie to the left? Anybody can put this on the chat if they want to. I'm just taking a break. Having a cup of tea. Well done, Ashley. Because in chemistry, the only thing we care about is products. Well done, Ashley. It's good because we have a greater yield of product. I'll write that down in a second. It lying to the left is a bad thing because we've got very little product. Now, this one is an interesting one. This one lies. It does lie to the right. Yeah, this one does. It does lie to the right. Lies slightly. I think that's very reasonable to put that. Slightly to the right. Slightly to the right, because I have more product. Yeah, we're always trying the second nota bene. Nota bene. Darn it. Nota bene. Because of the equivalence to the left, then there are lots of products and returns back to the reactants again. Ben has the right idea, but the opposite. Ben, you've got to remember that once you reach equilibrium, the products, the concentration of reactants and products remains constant. It'll then fix at that point. Yet you say, oh, because if it lies to the right, then lots of products are going to return. No, they won't. They're being made and destroyed at the same rate, Ben, which means it becomes constant. Nota bene. In chemistry, we are trying to make products. Bullet point number 1. Lying equilibriums What did I actually put? How did I put it? Lies. Yeah, okay. Equilibriums that lie to right make more products. Make more products. Yield is higher. So I now need to, now picking up my learning objective again, so it's this word yield. I need to make sure that this is really clear. Yield. Equilibrium yield is the amount of product, the amount of product made. Now this is the really complicated bit. Per pass. The reason being is, I know this is horrible. I'm sorry for this. Yeah. Yeah, per pass. The amount of product made per pass. The reason being is we recycle. Equilibriums are tricky because once it reaches equilibrium, you've got to remove the products because it stops changing. So they then take out the products and then we recycle everything back in that hasn't reacted. I need to, that's going to require me looking at that from a context perspective. So I'll do that in terms of Haber. Yeah, per pass. But the higher the yield, the better. Yeah. So if we just look at our, by the way, if we look at this graph, this is a poor yield. This here is poor yield. Why is it a poor yield? Yeah, the reason why it's a poor yield is at 6 minutes, equilibrium was established. Yeah, the reactants and products are no longer changing. And my product is smaller than the reactants. Yeah, we know that the product here, as a result of that picture, the reactants are greater than the products. This equilibrium lies to the left. Lies to left, and that's bad. Yeah, we're getting rubbish amounts of product, poor yield. Yeah, I hope that makes sense. I hope that makes sense. So I know this is difficult. I do. But these kind of basic concepts, I'm going to put that in a bubble. There we go, another note penny. So I'm actually going to leave it there for today. I'm actually going to give you no homework this time because, oh, actually, no, I didn't give you any homework last time, I don't think. But I'm actually going to leave it there for today because we're coming up to break time. I hope that all made sense. It will make sense, by the way, when we start putting this into questions. I've done my last learning objective as well. When we put this into questions, it'll make, why does one lean to the right? Oh, Ruby, what a great question before I end. Okay, why does number 1 lean to the right? Oh, Ruby, because it does. No, that's a bad answer. The reason being is because, wait, Mr. Dodd, doesn't 3 lie to the left? No, lies to the right. Number there. You're going to say because the total on this side is 8. Yeah, no, but it's not because each one individually is 4. I understand why you've asked that, Ben. So, yeah, it's not. It's because we started off with 10 G's and 10 H's and now got 6 I's. Yeah. Aren't you supposed to add the numbers reacting together? No, you're not. I don't want you to get too lost on that, Ben. Don't worry about it for now. I'll come to that because you don't need to worry about that until A2, so we can just ignore that for now. Ruby asked a really good question. So hang on a sec. What makes, so okay. Last question. What makes an equilibrium lie to the left or right? And the answer to that question is the conditions. Conditions. So we're going to do this next lesson, Ruby. Yeah, and what we will then realize is that actually we can actually shift the position of equilibrium. If I had an equilibrium, A plus B in equilibrium with C, and I have 8, 8, and 2, I know that that currently lies to the left. Lies to left. This is bad. Yeah, this is bad. Yeah, because I've got very little product, Yeah, but what I can now do is I can change the conditions. So I can now alter conditions. Now, the conditions that I can alter are temperature, I can alter pressure, and I can alter concentration. And what I can do is if I alter these conditions, alter conditions, I can push an equilibrium in, but how can you tell from the equation? How can you tell from the equation? You can't, Ruby. You've got to do it experimentally. You can't from the equation. The actual equation is going to be important to be able to understand how to shift it, but it won't tell you the numbers until you actually do it. Yeah. So if I change these conditions, if I change these, I can push an equilibrium either to the left or to the right. I can shift its position. Yeah, and we're going to be doing that next lesson. But how can you tell? Yeah, so okay. Right, I'm going to leave it there, guys. I need to turn my camera back on. It's never crashed, actually, when I've turned it back on again. I know, right? And then I can go start cam. Is it going to give me the forward one? Yes. Right, guys, I'm going to leave you there for today. I'm not going to give you any homework. I hope you guys have a nice weekend, because the next homework you will have, because we'll be changing conditions. Guys, I'll see you all next week. Have a nice weekend. Be safe. Take care.